Okay, now I want to stop, and then this is not where I started with the class, but this is where I kind of ended up. We had a lot of discussions about different things and then all the units. We're now going to be creating tanks and lifting liquids out of the tank, or we're going to lift them up to higher levels, or we're going to be lifting a lot of stuff, or we're going to be looking at the pressure underwater. So underwater or lifting oil or whatever. So the density of the liquid becomes important. So we've got the metric system and we've got the English system. And I want to talk about density. Now, density in the metric system, if we're talking real density, is either in grams per cubic centimeter, or in a bigger world where we're talking about larger things than just little lab type stuff values, it's going to be kilograms per meter cubed. And what I mean by that, we'll be talking about kilograms in meter cubed, which could be used to calculate volumes behind dams or whatever, bigger size units. Kilograms is mass per volume. Mass per volume. That's density. This is mass density. And if I'm talking about water, water's mass density is 1,000 kilograms per meter cubed. A meter cubed has 1,000 liters. And if you don't know what a liter is 10 centimeters, about 4 inches, by 4 inches by 4 inches box. It's a box about this size. 4 inches, 4 inches, 4 inches, 4 inches back. That's about a liter. It's about 4 inches. It's 10 centimeters by 10 centimeters and 10 centimeters and 10 centimeters. That's a liter. And a liter of water is kind of the standard of things. That's 1 kilogram. Or if you will, if you do 1 centimeter by 1 centimeter by 1 centimeter, called 1 cc, 1 cubic centimeter, or 1 ml, 1 milliliter is 1 cc, which is 1 cubic centimeter. And that was, if it's water, 1 gram of water takes up 1 milliliter. If it's not heated too much or whatever, it's kind of at cold temperature, like at 4 degrees, whatever. It changes slightly, but that's pretty much the standard for what a gram is. And since there's 10 centimeters by 10 centimeters, there's to be 10 boxes this way, 10, that's 100 times that, that's 1,000. There's 1,000 milliliters in a liter, and so if each milliliter is 1 gram of water, then a liter is 1,000 grams or 1 kilogram. And that's mass, not the weight. Okay? All right. So if we talk about water, let's write that up here. H2O is numbers for water. They will change if we do oil or gas or maybe water that's got hot chocolate in it or sugar in it, or Coke that has sugar, whatever, okay? Now, I want to talk about another thing. This is probably not the correct terminology, but I'm going to use it anyway. I'm going to call it weight density. Weight changes as you move away from like the Earth. Your weight gets less. If you move, it depends on the two masses that are attracted to each other. So weight density is not a good way to describe this. but it works well for understanding what we're going to be doing here with the calculus. So to convert mass, kilograms, to weight, we would have to be, kilograms is a mass times acceleration due to gravity creates force, which is what a weight is. So if we take this times acceleration due to gravity, the kilograms, it becomes kilograms meters per second squared over meters cubed. And this is what a newton is, so it's newtons per meter cubed. Newtons is a force, could be if under gravity, could be the weight per meter cubed. That's why I'm calling it a weight density. So much weight per meter cubed. And so what we had to do is multiply by gravity, which is 9.8. So if we're doing water, then it would be 9.8 times 1,000, or 9,800 newtons per meter cubed. That's the weight density of water. Now, the English system, if you read the book, they'll tell you that it'll be a force, which is weight, which is pounds per cubic feet. And they tell you, they just outright tell you for water, it's 62.4 pounds per cubic foot. It's already got, pounds already has gravity in it. If we wanted to go back, which we're not going to do very much of, but if we wanted to go back, let me do a different color here. I'll do red here, red pencil. If we wanted to go back to here, we'd have to divide by the acceleration in gravity, due to gravity, in feet per second squared, and that is 32 feet per second squared. And now the units for this was pounds per foot cubed, and so this would be how much the mass density is, and one of the feet would this would get a unit that's kind of strange, so we really won't be doing much with that, but that would be how we would get the mass density in the English system. Okay, so how are we going to use this? All right, let's start with a fairly simple. Let's take a cylindrical tank. Let's say it is 10 feet tall, has a radius of 4 feet, and it's filled up to a depth of 8 feet with water. And I want to pump the water out of the tank. So I got to lift the water. The pump that I'm going to use has to lift a slice of water. I'm going to slice this into a whole bunch of things, like think of a bunch of bread slices. And I'm going to slice it this way and not vertically, because that shape isn't very nice. This shape is really nice. And I'm lifting everything on this disc the same distance. Now, to do this, I need to set up a coordinate system. I have to decide where the x-axis sits in the y-axis, so I know what I'm doing. So for this, I'm just going to make the y-axis go right down the middle, And I'm going to make the x-axis, I could put the x-axis at the bottom, at the top of the water, top of the tank. Doesn't matter. Let's do it a couple times. Let's do it first at the top of the tank. So then I'm going to think of the positive y being down there. Okay? Not at the top. All right. So I've set up my coordinate systems. Here's the x-axis, here's the y-axis. All right. I need the volume of this disk, because I want to find out the weight of this disk. Weight is a force, and work is force times distance. So when I'm lifting something, I'm lifting a weight a certain distance, and that's how you're going to calculate the work. Weight times distance. So we're going to calculate the weight times the distance we're going to lift it. All right. Well, if I know the weight density, which is in feet, it's 62.4 for water for every cubic foot. So the weight would be 62.4 times the number of cubic feet. Cubic feet's volume. I need to know the volume of this disk. That's why we spend so much, another reason why we spend so much time on disk and shell methods. What's the volume of this disk? Well, the disk thickness is in the y direction, dy. Its radius is in the x direction. And so the volume of this disk is pi r squared, or pi x squared, because r is x, dy. That would be the volume times the weight density, which would be for water 62.4 pounds per foot cubed, cubic feet. X is in feet. Squared is going to be feet squared times the thickness is in feet. So I got feet times feet times feet. Feet cubed, we're going to cancel feet cubed. And I'm going to have weight of pounds. How much this disk weighs. And I have to take it times the distance I'm going to be lifting it. And the distance I'm going to be lifting it is going to be from here to the top. Well, if I make this the origin, from the origin to there is going to be y. Now, if I put the grid down here, that y is a little bit more complicated. Okay, so it's just going to be y. Now, that's how much work it's going to take to lift this particular disk. But I wanted to do all of the disks in here. The one below it, the one a little bit closer, and all the ones up here. All of these disks of water I want to lift to the top. Now, each of these disks is going to be a different distance I have to lift it. But they all are going to be pi x squared dy times this. So I'm going to add up the work to move all of these up y. So it's going to be pi x squared times 62.4 pounds per cubic foot. Then I'm going to lift y, and it's times dy. And I'm going to lift them how far? Well, the first ones I'm going to lift them, well, feet, 8 foot. The top of the tank is 10. It's going to be 2, a distance of 2 for the top disc. And the bottom disc, I'm going to lift all the way from the bottom up to the top of a 10-foot tank. So 2 to 10. That's going to be all the discs lifted to the top. Now, I could do this except for x squared and y I need to get it in terms of y. Well, if that's the x, what's the y value? Oh, it's the radius. Well, the radius isn't changing. So in this particular problem, since the radius is always 4, I don't need to use x. I can just put in 4. And if I do that, then this just becomes the integral from 2 to 10, 4 squared is 16, pi times 16 times 62.4, pi times 16 times 62.4 times y dy. Well, there's not much there that's changing anymore. The integral of y is 1/2 y squared, evaluated from 2 to 10, and take this answer times this, and I'll figure out the work done in the work would be, oh, I should probably say that up here. The work would be, this is how many pounds per cubic foot, so I'm going to take the weight density. We took the weight density times the volume. The volume gets rid of that volume and becomes just the weight. So this turns into the weight, or a force, times a distance. So the feet have canceled out when we multiply by the volume. We get pounds times the distance, which is going to be feet. And so my work is going to be foot-pounds. In the metric system, it becomes joules, like I did on the previous assignment. Okay, so I'm going to get 100 times a half, 50, minus 4 times a half, 2, times all of these constants. And that would give me the number of foot-pounds of work, lifting the water out of that tank. Okay, now let's do another one. Let's empty a conical tank. Let's say the tank has a height of, we did 10 feet. Let's do 10 meters on this one. Let's do this one in the metric system. And let's say the radius is, if that's 10, this might be 6-meter radius. Okay. Let's have it filled with water. Let's make it completely filled, but we need to lift it up to pour it into something, so we need to lift it up an extra 3 meters. Now, where do I want to put my coordinate system? We can put it any place. Last time I had it at the top of the tank. I could put it up here, or I could put it at the bottom tank. I'm going to put it at the bottom tank this time, just for the fun of it. I'll make this my x-axis, and this my y-axis. And now I'm going to take my representative slice. Since this is a cone, it'll be a disc again. And the thickness of the disc will be a dy. And this will be the radius, which is in the x direction, so it's x. So the volume of this disc is pi x squared dy. And if you take volume times the weight density in the metric system, we're going to take the volume, this is the volume, the weight density of water in the metric system is 9800 newtons per meter cubed. And this would be meters times meters times meters, meters cubed. So now we're down to newtons, which is a force, the force of the weight of that disk, times the distance, this is the weight density, and we're times the distance, we're going to lift it, D-I-S-T-A-N-C-E. Force times distance. And the distance I'm going to lift that is going to be from here to there. But if I make my coordinate system here, this is y. If that's y, that's not how far I'm lifting it. If this is 10 from here to there, and this part is 3, then the distance I'm lifting it, which will be from here, there to there, is going to be 13 less y. 13 minus y. That's the distance I'm going to lift that disk. 13 minus y. So I'm going to have to lift this one disk. The work done to do this one disk is going to be 9800 pi. See, we got to do dy. So x. How am I going to get x in terms of that? Well, I'll just write it x squared, and then I'll do 13 minus y, and then I'll put my dy at the end. That's the way we like to do it. And we're going to do all the disks from here, the top one, all the way to the bottom. That bottom disk has to go how far? Well, y would be 0 here, and y would be 10 here. We're going to go from 0 to 10. Now, see that if I put in 0, that bottom is going to be lifted, 13 minus 0, it's going to be lifted 13. The one at 10, 13 minus 10, is going to be lifted 3. Do you see how this is going to correct for the distance I'm lifting it? Each one of these, all the disks that are in here. The only thing I have left to do is get rid of that x. And I can do that a couple ways. I might see similar triangles in here. The similar triangles I see are yx here and 10, 6 there. And I'm trying to replace the x, so I'm going to start with x. X is to, say, 6, as y is to 10. Ratio of similar triangles. I'm trying to get the x out of there, so I need to solve for x, so I'd multiply by 6. And 6 over 10 is 3/5. So x equals 3/5 or 0.6 y. So I'd put this in place of my x squared, type the whole thing into calculator or distribute that, pull the constants out, but I got to square it and then distribute it, and I can integrate it and find out how much work it takes to lift all the water out of this tank up to a height of 3 meters. All right. Let's see, do I want to do another one? I'm going to pause this and then do another one.